Hello there. In this chapter, I will introduce you to the concept of testing in programming. We will discover what is testing in programming in general and also some aspects like tests and test cases. As you can notice from the first chapter, where we code a Hello World program, in this series about programming in Go, we will write a lot of tests for each code sample we will have, following the test-driven development way. That's why it's very important to have a basic knowledge of such things as tests, test functions, test cases, etc. Firstly, let's start with definition of testing in programming. Testing in programming is the process of verifying and validating a software to ensure it works correctly and meet requirements. In simple terms, testing in programming is like a checking your homework to make sure it's perfect. It's a careful process where you try out different things to see if your code works correctly. It doesn't have any mistakes. Just like you would review your answers before turning in your homework, programmers test their code to catch any errors and make sure their software works smoothly for people who will use it. In practice, testing is the process of writing tests for the code which we want to check it works correctly. So what is the test then? Test represents a structured examination of software, a program code, and aims to validate its operational correctness. Simply put, a test is like a little challenge we give to our code. It's a way to see if our code works properly and does what we want it to do. To define what is test more specifically, Firstly, we need to know what there are several types of tests in programming. There are three types of tests. First, it's a unit test. This type of test focuses on testing individual units or components of code in isolation. Unit tests validate small section of code, typically functions or methods, to ensure they produce the expected outputs for given inputs. These tests are fast and provide quick feedback during development. Second, it's integration tests. These types of tests involves testing in the interactions and integration between different units or modules of code. It ensures that various parts of software cooperate effectively. Finally, the third type of test is end-to-end test. These tests simulate real user scenarios and interactions with the software, validating that the entire system behaves correctly. While comprehensive, these tests are typically slower and more complex to set up. These three types of tests form what is known as the testing pyramid. In turn, the testing pyramid is a framework used in the software development to guide the distribution of different types of tests based on their scope and efficiency. Tests that we're going to write in code examples are unit tests. In Go, it's basically a function, a name block of code that performs a specific task or operation. This type of function, which represents tests in Go, is also called test functions. Now let's put it all in practice with an example. Go back to the sandbox folder which we created in the previous chapter. Here, in the root of the folder, create a new folder called calculator using command mk directory, or you can create it in the code editor of your choice. Open a new folder and create a new file called calculator.go using command touch in the terminal. You can of course also create it in the code editor. After that, just open the file in the editor. As we learned from the first chapter, we need to declare a package in the file. Since we are going to write a part of a functionality of a regular math calculator, as you can tell by the name of a folder, we will declare this package as a calculator. Write package declaration line in the calculator.go file. Great! Now we need to create another file that will include tests for functions in calculator package. In the same calculator folder, just create a new file called calculator_test.go. As you remember from the first chapter, where we created a Hello World program, it is important to name a file with tests as x_test.go, where x is the name of the file that contains code which tests are written for. In our case, it is a calculator.go file, so we need to name file with tests as calculator_test.go. Open the file in the code editor and write the package declaration line. In this chapter, we will write a function that summarizes 3 numbers and return the result of this operation. Very simple function, isn't it? Just to cover up the main concept of testing for the code we are gonna write in this series. Okay, now before writing the test itself, which in our case is a test function, we need to tell Go which packages we need to import to use functions from it. In every file where we write in test, we need to import package testing, which includes necessary things to run tests. Next is the package calculator, from which we will use function sum to test it. Because package is the Go module called sandbox, we need to put the prefix sandbox before name of the package. Now it's finally time to write a test function that checks the correctness of the function sum. First of all, declare the function test sum. Again, as I mentioned in a previous chapter with Hello World example, there is a convention for naming a test function which looks like test x, where x is the name of the function that we want to test. Great! Our function sum should take 3 parameters, all with the same type, int, which stands for integer number. So we need to declare 3 variables that contain values for all 3 arguments of the function. In that case, I'm gonna name these 3 variables as a, b, and c. The same name will be used for parameters of the function sum. For this example, I will use short variable declaration, which I also mentioned in the chapter Hello World. In the chapter about variables, you will learn about our types of variable declaration. These 3 variables represent so-called input data for the function we're going to test. While writing test, we need to make sure we prepare input data for the function we're testing if the function takes any parameters. For example, in chapter Hello World, we wrote a function Hello World, and since it didn't take any parameters, we didn't need to prepare them in the test. The case with function sum is the opposite. The function takes 3 parameters and we need to prepare them in the test so we can call it in the test function, and Go will compile the code of test without falling with an error. Okay, since we have input data as 3 variables a, b, and c, the next thing that we need to declare is a variable called won't that represents a value that we are expecting the function returns as output data. The function sum should return a value with the type int, which is the result of the summation of all 3 arguments a, b, and c. The result of summation of values in our variables a, b, and c equals to 6, so we will have declare and initialize a new variable with this number. The last thing what we need for this test is to call the function sum with variables a, b, and c as an arguments and store the result of the function execution into a variable called goat. We need a variable goat because we're going to compare its value with the value of a variable won't. If they're not the same, then the test should fail and print the message telling the returned value of the function sum is not the same as the expected value, which means that the function does not work as we expected. By the way, if you are using code editor with some code inspecting, such as VS Code or golang, you might notice that the function sum has a red underline or another sign of the error. Just don't worry about it right now, as at this point it's normal and we will fix it later. Comparing the result function execution with expected value as the main part of the test. To print a message about failing the test, we need to use function from package testing. which we already imported above. The function is called trf and it takes several parameters. First one is the message that should print in the terminal in case when the test is failed. That message can include so-called formatting verbs, special substrings which will be replaced by values that are specified as second and further arguments of function rf. We already used this function in chapter Hello World. Now, when you prepared all input data that is needed to call a tester function and wrote the whole test for that function, you're wondering what the next step is. And the next step is to get to know the concept of the test during development cycle and test during development mantra. These concepts were touched on the chapter Hello World. But before diving into it, it's important to know that test during development cycle and mantra are parts of the more common concepts such as test-driven development or TDD. Test-driven development is a software development approach where you first write tests that describe how your code should work. This process helps ensure that your code works correctly and remains reliable as you add new features or make changes. As you can see, we already followed that way while implementing the calculator feature. We wrote the test first before writing the code for the function sum. Test-driven development includes the so-called test-driven development cycle, which was mentioned before. The test-driven development cycle is a repeated process used in software development to ensure high-quality code and reliable software outcomes. It consists of specific steps. The first one is write a test. Start implementing the feature by creating a test that defines the behavior you want to implement in your software. This test should initially fail since the code to fulfill this behavior hasn't been written yet. This step we already made by writing a test for a function sum, even if this function does not exist yet. The next step is run the test. You need to execute all existing tests, including the new one you just wrote. This step confirms that the new test indeed fails, validating that your testing environment is functioning correctly. Since we have made the first step, now is the time to make a second one. Open the terminal and open the folder calculator in the project root folder if it's not opened yet. Now run the command go test to run all tests inside the package folder. In the terminal you will see that test failed, but it is not a failing that we are expecting from the test if the result of executing the function sum is not the same as our expected value. The test failed during the compilation. The Go compiler couldn't compile the test because the function sum from the package calculator is undefined. It does not exist yet. To fix that problem, we need to at least declare the function sum inside the package calculator, and that is the next step in the test during development cycle. So the third step is write code. Develop the necessary code to make the failing test pass. This code may be minimal, focusing solely on making the test transition from failing to passing. We don't actually need to implement the whole logic inside the function sum. At this point in time, we should only write a so-called null implementation of the feature just so Go compiler can compile the test and it will fail because of the logic we wrote inside the test. Open the file calculator.go in your code editor and declare a function sum. We didn't write anything inside the function yet. In this step we can rerun test again to make sure that test will pass. In the terminal, run the command go test again. As you can see, now we have another type of error, which means we fixed the earlier problem in our code, but we still need to write code so the Go compiler will at least compile the test. The problem now is that we're calling the function sum with arguments, but we didn't specify any parameters in the function. So let's fix that. Open calculator.go again and specify the necessary parameters. That's how we can specify parameters of the function in Go. Notice that if several parameters of the function have the same type, you don't need to specify the type for each parameter. Since all three parameters a, b, and c have the same type int, you can write it in the end of the list of parameters. Great, now let's rerun test again. We fixed the previous problem, but we still have things to do to make Go compiler satisfied with our code. Now the problem is that we're expecting the function sum to return some value in the test, but the function sum doesn't return anything. Do we need to write our whole logic inside the function sum? Our task now is to create a placeholder or minimal version of function that satisfies the syntax requirements but doesn't contain the actual logic or functionality. In other words, we need to write null implementation of the function sum. Null implementation is needed to check that test fails when the function returns the wrong result. If the test fails, then it means that this is written correctly. Okay, let's do it. We specify type of returned value of the function as int. We also wrote that the function returns the number 0. It could be any other number, but it's unspoken rule to return a so-called default value of the type, and for int type it is 0. Now it's time to rerun test again. Great! Now Go compiles the test and the test fails because the function sum returns the value not the same as we expected in the test. You can see it by the message failed, expected 6 but received 0. Good. We can finally write the logic for the function sum and finally make test pass successfully. As you remember, our function sum should return a summarization of three numbers in arguments a, b, and c. We can add up numbers in Go by using the operator plus. Run test again. Great, the test has been successfully passed. However, there are few more steps in our test-driven development cycle. The next step in the cycle is run test again. You should run all tests after adding the new code. Because the test you previously created is not successful, this stage guarantees that your modifications haven't unintentionally caused issues in our sections of the code. So basically, we already completed this step, and we can go to the next one. Since all tests are passed, it's time to do a refactoring. And that's how this next step is called. With the test successfully passing, you can refactor or optimize the code you've written while maintaining its functionality. Well, the thing is that there are not many things we can refactor in our simple function. However, we can refactor the test to make sure that function works correctly in a different scenario. In that scenario, there can be different input data to pass in the function sum. Do we know how the function sum works with different input data? Of course, our function is very simple and basic, since we are depending on how adding numbers works. But anyway, what if we will change the function so the return value from it will be different than the value we are expecting? It's good to test the function not in one but at least in a few different scenarios, and that is called a test case. A test case is a specific scenario or situation that you define to test a particular aspect of your program code. It consists of inputs, expected outcomes, and conditions under which the test is conducted. In other words, let's call the function sum with different input data in the test. There are several ways to write a test case inside test function in Go, but the most popular and handy is to write so-called table test or table-driven test. A table-driven test is an organized testing method where test cases are listed in a table format. Each row in the table represents a different test scenario, and the columns define inputs, expected outputs, and other relevant parameters. In practice, to write a table test, we need more advanced knowledge of Go than we have now. To write a table test, we need something that will look and act like a row of the table. In a row, we have columns, and each cell of the column includes some information or data in our case. What data do we need to test the function sum? Well, obviously, we need all three variables a, b, and c, which represent input data of the function. Also, we need a value that we're expecting to get from the function. We store it in a variable called want. Great. Each of these variables we can imagine as columns of the row, columns a, b, c, and want. In Go, we need to define a type for the variable we're gonna declare in case if this type does not exist in the first place, like types int, string, and bool. So basically, we need to define some type for this imaginary table with columns a, b, c, and want. In Go, there is a special data type called struct that can be used to group together different fields with potentially different data types under a single entity. That's exactly what we need. To make struct definition, let's use a special keyword in Go called type. In the file calculator_test.go, remove all code block inside the test function test sum, since we don't need it in that way. Instead of that, we're gonna write a table-driven test. Good. Now write a struct definition called test case inside the test function. That's how the struct definition looks like. We defined the type with name test case, and it's a composite type. Now it's time to specify our so-called columns inside the struct test case. Great, we told Go that we have a type that represents a test case. If we declare a variable with type test case, it will include values of fields a, b, c, and want in one place. So instead of having several variables with data a, b, and c, and want, we can store values inside one variable. But we don't need just one variable for the test case, because we need at least a few test cases in our test. We need a list or a collection of test cases. And we can do that in Go using a slice. A slice in Go is a flexible list that can grow or shrink as needed. It's like a dynamic array without a fixed size. In turn, an array in Go is a fixed list of items. The number of items doesn't change after you set it. Now let's see how we can create a slice of our test cases. Next, we will loop through our test slice, executing each test case one by one. This approach ensures that our sum function is tested against various scenarios. By organizing our test into a slice, we can easily add, remove, or modify test cases, making our testing process efficient and maintainable. After we structure our test cases inside the test cases slice, it's time to use them to test the function sum. But how do we systematically go through each test case? The answer is using a loop. A loop in programming is a construct that allows to repeat execution of block of code based on a specific condition or set of conditions. In Go, a loop is primarily implemented using the for keyword. Unlike many other languages, Go doesn't have while or do-while loops. Instead, it utilizes different forms of for loop to handle all iterative processes. Whether you're running a loop for a set number of iterations or based on condition, Go's for provides the flexibility to manage it. Looping over some list of data is like telling the program for each item in this list, do something. Let's see how it works with our test cases. Here we're telling Go to iterate through each test case in our test slice. For each test case, we calculate the result using the sum function. If the result is not what we expected, then an error is reported. By using the loop, we can automate the process of testing various scenarios, making sure our sum function behaves as expected across all of them. Let's run our test now to ensure our sum function behaves as expected. All tests have successfully passed. Okay, now once we implemented test cases using structs and loop in our test, there is still a few things to improve in our test code. But before that, let's change some test case values so the test will not pass. For example, let's change a value of parameter b in the second test case from 5 to 9. Okay, and now let's try to run test again. As you can see, test is failed, which tells us that test actually works correctly. Here in the output in the terminal we see that each test case is failed, with one which has 4, 9 and 6 values. We also see which value we expected here and what we actually got. It's all good, but what if we want to change the function that they're testing, which is function sum, to make sure that the test case with value 4, 9 and 6 pass, or we want to fix values in this test case because we actually made a mistake while writing the test. In both scenarios, after changing the code and running command go test, we will see that Go testing framework ran all test cases, even ones we don't want to change. You can actually split tests into subtests, and in each subtest you can run a test case. By doing that, you will have an ability to run one specific test case inside a specific test function instead of running all test cases and all test functions. In this example, we have only one test function and several test cases, but in real project you can have dozens of or hundreds test functions and test cases in one package. So an ability to run one specific test in test function can be very useful. To write subtests in test functions in Go, you need to use function trun from the parameter t of the test function. Let's see how it works in practice. Inside the loop 4, call function trun so it will be executed in each iteration of the loop. The first parameter of the function trun is the name of the subtest. This is a string type value. You can write there something like test case number n, where n is the number of test case, but what can be more useful is to write a string with values of each parameters a, b and c from the test case. We actually already wrote this string in the first parameter of function trf, so let's just cut it and put inside the first parameter of function trun. By doing this, we clear the output of function trf because it should only print an information about why test and test case did not pass. Need to mention that function trun doesn't work with formatting verbs as function trf do, so if we want to use formatting verbs and set a string value for the first parameter, we need to use function like fmt_printf. The second parameter of the function trun is a callback function. We can wrap whole code block inside loop into a callback function for the second parameter of function trun. There is a one parameter of this callback function, the same as parameter of the test function, a t parameter, which includes various of Go built-in testing frameworks methods. Okay, now let's try to run our test. As you can see, the output seems a bit different. Now command go test prints an information about which test function is failed, and also which test case is failed. We see that test case which has parameter A as 4, B as 9 and C as 9 did not pass the test. Alright, let's say we changed some values inside failed test case, or we changed the function which we test and we want to rerun this specific test case by using go test command. How can we do that? All we need to do is just to specify a flag run for the command go test. A value for the flag should look like this. The test function name is the name of the test function we want to run. In our case it's a test sum, and subtest name is the name of the subtest which we want to run. In our case the subtest and test case are basically the same thing, and the name of subtest be specified in the first parameter of function trun. So we finally need to write something like this. As you can see, we successfully run the specific subtest to make sure that other subtests, the same way test case, didn't run. Then we call command go test, we can put function fmt_println here. If we run command go test without flag run, we will see the output of function println as many times as we have test cases, which is 3. If you run command the flag run, you will see only the output of function println only one time. Okay, good. Let's fix values in second test case, so the test will pass again. Okay, we've completed the refactor step in our test-driven development cycle. Now let's move on to the next and final step, repeat. In this step, you should return to step 1 and create another test for the specific piece of functionality you intend to add or modify. You have to follow the cycle iteratively. Write the tests, run tests, expecting the new one to fail, write code, write tests, expecting all tests to pass, and refactor if necessary. Since we don't have any additional functionality to introduce for our sum function, we've now successfully completed the test-driven development cycle for it. Besides the concept of test-driven development cycle in TDD, there is also an essential guiding principle known as the test-driven development mantra. The test-driven development mantra is a concise representation of the core TDD process, and it's often expressed as red-green refactor. Test-driven development cycle and red-green refactor mantra are closely connected, as the mantra simply outlines the TDD process steps. Red corresponds to the initial phase of the TDD cycle. The developer writes a test for a new piece of functionality. At this point, since the functionality hasn't been implemented yet, the test is expected to fail. This failing test sets a clear goal to implement the functionality so that this test passes. Green aligns with the next phase of the TDD cycle. Here, the developer writes just enough code to make the failing test pass. It doesn't have to be perfect or efficient, it just needs to satisfy the test requirements. Refactor corresponds to phase where the developer reviews the code they've written. Now the test is passing and refines it. The goal here isn't to add new functionality or to make instead, the purpose is to improve the code structure, readability and possibility performance without changing its external behavior. If you ever find it challenging to recall all the steps of the test-driven development cycle, just remember the mantra red-green refactor and use it as guide when writing tests. After successfully implementing our feature with TDD, it's good time to answer a common question. Why is writing tests and adopting TDD so crucial when coding or exploring a new programming language? Firstly, TDD offers a systematic approach to coding, urging you to focus on the what requirements before the how implementation. This method ensures clarity of purpose and robustness in the end result. Secondly, the immediate feedback from passing or failing tests offers a continuous learning loop, validating your understanding and highlighting areas for improvement. For those diving into a new language, this feedback is instrumental in decoding unfamiliar syntax or concepts. TDD is not just about writing code that works, it's about writing code that's reliable, maintainable, and testable. The last thing I want to introduce you is the concept of code coverage. So, what exactly is code coverage? Simply put, it measures how much of your code is being tested by your unit test. It gives you a percentage that represents how much of your code is checked or tested by your automated tests. In Go, we often aim for high code coverage to ensure our functions and methods are behaving as expected. The more of your code is covered, the more confident you can be that it's working as expected. But remember, while a high coverage is good, 100% doesn't always mean your tests are perfect. It's the quality of test that truly matters. There are different types of coverage that focus on different pieces. First one is a line coverage. How many lines of code are tested? Second is a branch coverage. Are both the if and else parts of your code tested? And function coverage. Which functions or methods are being called during tests? Alright, let's dive into a practical example. Open the folder of package calculator again in the terminal. To measure the test coverage in Go, you can make use of the built-in tooling. Just run the command. This command gives you a percentage of how much of your code is being tested. As you can see, in this package calculator, the code coverage is 100%. It means that we covered all lines of code in the package by our tests and test cases. Sometimes the output of the command Go test cover doesn't give us enough information. For example, we cannot see exactly what lines of code are covered or in function that we tested. We can look at more detailed information about covered lines of code using combination of these two commands. First command will generate a special file with information about coverage and uncovered lines of code. The second command converts this generated file into another one with HTML code and opens it in the browser. As you can see in the browser, there is detailed information about covered and uncovered lines of code in the package calculator. Green lines of code represent covered lines of code. It means they wrote enough tests to check how these lines of code work. While a high test coverage percentage can give you confidence that many parts of your code bases are tested, it's not an absolute measure of the quality of your tests. For instance, you might have a high line coverage but low branch coverage, indicating that certain logical paths in your code aren't being tested. One way or another, we will use code coverage to understand if there is enough tests that check lines of code in our examples. Alright, that's it for today. See you in the next chapters.